Bueno, muchas gracias a todos por venir.
Thank you all for joining us. We'd like to thank Rooted, and we're going to talk about cache memory and syphilis. Did you think it was the name of a tool, syphilis? No, no, no. We're going to talk about the disease. Nietzsche died out of the disease. This is a disclaimer of the presentation. The motivation for those knowing me well, what I did love, what I still love is web security, navigators. And back in 2016, I read this paper, How to Attack the CPU, the cache memory, and using the Java environment. And I was missing many things because I thought that to control what happened at the CPU level was impossible. Here we treat this, we try to shed some lights on some things we take for granted, and let's see what we can do. Let's start now. Let's start into the core subject. Here you see, this is a processor. It's an Intel Core 4th generation. It's a hashware family. And basically it shows that cache memories, cache latencies are important, and it takes a lot of surface space. And you know what is a memory cache, but to say it in simple mode, the problem is that we have CPUs working at very high frequencies, and that means that there is a problem. CPUs, they had instructions, and we forget about memory instructions. And when you have high speed, the CPU should wait 200 cycles waiting for the order, the memory instruction to do whatsoever. And to solve this, they introduced a hierarchical approach regarding cache memory issues. They have smaller memories, small cache memories closer to the CPU and faster and more expensive. In most of the CPUs of the high level, we have this hierarchical structure. What I'm going to say is based in the case of Intel environment. You could use other processors, but we're going to talk about Intel. We have cache memory hierarchical approach. Inside each core, we have the first, the second, and the third one is shared among the 3 cores. And that allows us to have, if a CPU would need to get some information, we get enhanced performance. We don't have to wait that long. So it is hardware that is controlling the memory and to have the necessary things inside the cache memory. That as an introduction. Anyway, my presentation will have 3 parts. Firstly, and I'm going to be very fast, we're going to talk about some attacks to motivate what I'm going to say. Have you heard about Spectre? And this is the first part of a presentation. And second thing is we're going to focus on a common problem we have and to see the relation with syphilis. We will see the diseases related to the attacks, and then we're going to talk about how can we do it with JavaScript. I'm going to skip row hammer to stick to the time, allocate it, and we're going to talk about Spectre. And this is a very ambitious slide, but let's see what happens. What you see here is the pipeline of a modern processor. And then basically when we want to execute whatsoever, we need to fetch the instruction, and the CPU should wait 200 cycles more or less. So what we do is trying to have the instructions there at the cache, level 1 cache memory. If we have to have instead of 200, we have 5 cycles of latency, and we do not need to wait so much. We have here certain ports of execution, and each port will have access to certain execution units. One execution unit is able to compute whatsoever. There are executions for arithmetic operations, floating points, big data, whatever, memory access and thing. So in each memory cycle, we can operate in parallel at each port if we want to maximize the use, the throughput of the CPU, the number of instructions that could be taken by cycle. we need to take all the ports. If you execute this one by one, that couldn't be possible, mostly because in general in one instruction we can occupy more than one port, but instructions, that is, instructions in general, they go through this, they are decoded in some micro-instructions, and this is what a hardware will execute. A micro-instruction, an instruction of the assembler, a pub, two instructions. One is memory load, and the other one is updating the start thing. So what we are interested in is to maximize the number of things, number of parallel ports we use, and to optimize this, they said same thing. Instead of doing instruction by instruction, we can execute them in whatever order, randomly. We decode, we fetch as many instructions as possible, a bunch of instructions, and we have a buffer here. And we have the reorder buffer, 224 entries, as you see here, 224. And the hardware is going to try to look for instructions if they can be randomly executed in whatever order. The only instruction is that results are committed. Results should be validated, committed, modified, the architectural structure in order of the execution of the program when we run the program. So the hardware will check this. Every instruction has an operand that depends on the previous instruction. We cannot execute the instruction because we have to wait for the previous instruction to be executed. But if two instructions are not related, it's irrelevant. We can do it out of the program order, and then in the reorder buffer, they wait till they are retrieved in order. Then we maximize the throughput of the system. And the state in which one instruction has been executed but haven't been retrieved. So the state is not manifested to the architectural world, to the registries of the system. It's a transient execution, transient mode, transient. But our problems are not only in instructions. We have the branches. Branches is with which we implement loops, whatever. And when we have a comparison where one of the elements depends on the memory access, CPU wants to know which to be executed. If we wait 200 cycles and we get the memory information, then we solve the comparison. That is once again another bottleneck, because we have a CPU that's extremely potent and it's there latent. And they said, let's try to predict how this how this is going to take place. And we have the branch predictors. The branch predictors, when you have a branching, the CPU will, and here we have a branch prediction unit. Then they will ask the prediction unit to see if there's going to be this jump or not, this leap or not, and we speculate, we take the instructions in sort of an order. Now the instructions are executed, and they are waiting at the reordering buffer, and then two things might happen. The predictor might be right. In that case, we retrieve the instructions from the buffer, and we've enhanced the throughput, or it could be wrong. If it's wrong, what we do is we discard instructions that were executed, but they are useless because the prediction was not correct, and we go back to where we should go. There is a small penalty, so to speak, but in the end, the branch predictor has a rate of success that's high. And as we program, the branch predictors are easy to implement. If you look at a loop, you will always consider the loop. It's a branch predictor saying you take this jump. It's better than not having any branch predictor. That's more or less an idea on speculative prediction. What happened with the spectra and all the things that they were talking about, the end of the world? During the execution, speculative execution, if it was not correct, even though we might discard instructions executed, the thing is that there might be traces in the microarchitecture. And what about traces in the microarchitecture? Normally, The simplest example is that speculative execution, even if not correct, might modify the status of the cache memory, and the attacker might see the cache memory and know things, learn about things. So let's take a look about the variant 1 of a spectra, the simpler variant of a spectra. But we have here a function. This is the assembler, and we have the offset. We compare with this array size, and if it is within the range, we have access to this position. The value is used as an index for the second array. And this 64 is just because it's a convenient thing. And what the attacker will do, he will invoke the victim function, and what happens, the branch predictor then will be trained to say this is not to be taken. If you look at the assembler, if we take this jump, we say it is out of range, so we're not going to take this branch. And we train the branch predictor, and what happens is that the attacker will make sure that the array contents are outside the cache memory with instructions, special instructions. And what happens is to invoke the victim function with an offset that is out of range. What will happen now when we're executing this? Well, we're going to compare, we're going to establish a comparison, and here what happens is that the array 1 size might be inside the cache memory or not. The comparison will take place soon, and then the speculation window will be very narrow. Nothing will happen, but the attacker made sure that the array 1 is out of the cache memory. When the CPU gets there, it will take 200 cycles to solve if the branch is going to be taken or not. During that time, we have to execute the whole code speculatively. And when we're based on that, we'll have access to the array 1 with an offset that is out of range, and we will have a value to which we shouldn't have access. We access to the array 2. And then with this access to the array 2, even though it's going to be discarded, it's going to be too late, because this access has provoked that a memory block was introduced into the cache memory. So the prediction was not correct. We discarded the instruction, but the cache memory was modified, and the attacker is going to measure the access time to array 2 offset 0. Offset 64, offset 128. When he detects the time is short, it is inside device by 64, and see the out of range value of this array 1. It looks like artificial, but there are gadgets with the patterns in whatever code, and the attacker could, if the attacker identifies the function this way, the attacker can read all the virtual memory space. And in JavaScript, where the attacker could have a JavaScript that will trigger those patterns, will be a big problem in JavaScript. So that is Spectra. And you have seen that the cache memory plays an important role, and here we're going to see in detail the way a cache has been organized. Regarding the cache memory, the cache belongs in different blocks. Instead of having a bytes memory, we have blocks. Each block 64 bytes. In this example, 16 bytes. The cache memory is divided in cache sets. You can see here 4 cache sets, and each cache set will have the capacity of storing the number of blocks association. We have 4 cache sets with association 2. If we have 4 cache sets, that means you need 2 bits to direct, to identify, to know that, because memory blocks will belong to 1 cache set, so you need 2 bits from the memory address to know where the block should go, into which cache set. In some cases we have virtual address, in some other cases physical address, and we're going to be based on that. The physical address is used to map a memory block into a cache set. What happens, obviously, there are very many more blocks in the memory than you have in the cache set, or in the cache. Many blocks will compete to be stored there, Here we have block 0, block 4, block 8, and they're mapping cache 0. And at the moment when we have two of those and we have to try to access to a third, cache memory should have to decide which is going to be rewritten on or replaced. We have the replacement policy. Replacement policy is trying to exploit. It's going to use rules at LRU. It's least recently used. The least recently used. Los bloques, that means that have been used recently in the least way, so we have to maximize the efficiency. Another way to look at real examples, we have this cache memory, 6 megabytes, and how many two-way cache, how many we have 6 megabytes, and then the capacity per cache set is 64 bytes multiplied by 12 blocks per cache set. That means we will have 8,198 cache sets. That means we're going to use 13 bits from the physical address to map a memory block onto one of those elements. Firstly, the 6 of those are the offset within the block we're going to discard because they are those having a lower specific weight. And then we decide about the index of the set. In the modern cache, the last level, there is an additional partition that is slicing. Instead of having one cache of 8,192 cache sets, it's best to have 4 or 8 slices to partition this, to splice, to have parallel access and to enhance the broadband. And we have, instead of 1 of 8,192, we have 8 of 1,192 each. So it's easier and we need less information to have an indexation. We have 6 bits as an offset, 10 for the set index, and to which slice this will go is to be decided by hash function that will use all the bits of memory. And basically there are some people having reversed engineering processes, but to go to the same cache set you have to have the same slice and the same bit. And with this we know already the way the cache memory is organized. An example of the attacker is a prime and probe, and there are very many variants, but the idea is the same. And in this case, what we're going to have is the attacker. We're going to have the attacker that will start with the priming. It is put in the cache at a known state. How can you use the priming? The attacker has to identify memory blocks that goes into the different cache sets. Let's imagine you have a cache set with 2 sets. You can more than 2, but the attacker is interested in those 2, and the association is 4. So we have 4 addresses going to the first set and 4 going into the second set. Once he finishes this, the cache will contain only the blocks introduced by the attacker. Then the victim. If the victim is executed as sensitive code of a sort, where the pattern of access to the memory will depend on some secret. In this case, if the bit I is 1, it's an access to the memory. The access means we have a memory block that's going to be introduced into the cache memory. After the execution, the attacker will give a try to see the changes that are taking place. The attacker will measure time, having access to the same blocks. If it's a short time, the block is still there. If it takes a long time, you have to go to the memory. The execution of the victim system has replaced one of the blocks, and you get a trace. It is not detailed. You don't know specific access to the memory, but if you have enough cache sets, you will know which is the relative access that has been conducted, and you have to differentiate among 2 types of execution, even though that looks crazy. And the truth is that it is used to breach, to breach even elliptic curves, and it has been implemented to see the number of pulses, the number of requests that have been used for covered channels. There was a very interesting conference years ago for the covered channel. Instead of one victim, you have two attackers that are cooperating one with another, and the cache memory is used to communicate, to send information. There was a conference where there was a protocol correcting code and so on, because there is a background noise there. There were protocols, a very effective protocol allowing two machines, two virtual machines, sharing the same hardware to communicate among themselves throughout SCH. It was a transport layer on cache memory, and then SCH, and they had streaming on SCH. You see the capacity of information that can be coded in the practical environment. So, and that's it. That's the first part of it. And I know you don't understand, but we want to motivate you, telling you the type of attack that might take place. That's enough. It is quite clear that if we have access to the virtual address and you have special instructions where you have to load whatever you want from the cache memory, our life is easy. You also have special clocks to measure time accurately, so you have to determine access to the cache memory. In other environments, it doesn't happen in a script. We don't have an idea of pointers, virtual address, and you don't have information to find the blocks going into each cache set. How can we use row hammer? The row hammer is retrieving content from the cache memory. How can we load the range, length, and how can we destroy this to open the window and to use spectra? Or how can we put the cache memory into a controlled state or probe it? The solution is eviction sets. Eviction sets. We're going to talk about eviction sets, a couple of definitions and one formula that we're not going to explain. Two addresses are, we see here, congruent if they map into the same slice set and the same cache set. The slice, if this is a physical address, we have to know this, and the set, it is part of the bits we said. You discard the 6 bits of that are lighter, and you determine, as we see here, the rest. One eviction set is just a set of addresses containing associations of congruent or consistent addresses. Consistent, it's written congruent there. Consistent addresses. So you make sure that V is not part of the cache set. It has been evicted, kicked out. That's why it's called eviction set. And we have put this, we have used inverted commas. You make sure that the V is not inside the cache set. Even though we haven't got any information on the physical address, and we do not know if two are consistent, two addresses are consistent, we have the experiment, which is the following. If we have the victim address, what we do is we have access to this victim address, we take the eviction set, a candidate set, and we have access to all addresses, and we measure the time we take to access the victim address. So it's still there. So our candidate set is not an eviction set. If it takes a long time, that means we have kicked out the victim. We have then, as we see here, and can you follow me? We have then with this idea, it is obvious that any sufficiently large set is an eviction set. If you have an 8 mega cache, well, you have random addresses, but there is no control. You will need a small eviction set. That means containing directing associations with the addresses. How can we find the minimum size of eviction sets? How can we do it? How can we get this minimum. And this will depend on the amount of information we had on the physical address. And we're going to see it with an example. The formula is simply for trying to give an idea. Let's imagine something.
So we have an attacker with 8 slices cage, 1,892 cassettes, and this means associativity of 12. So we have 4 QBs per pages. So this system uses 4 QB system. So 4K pages is interesting for us because when you translate from virtual address to physical, the pay offset will be identical of the 12 bits that are heavier. So most of them are going to be random as well. So an attacker that can control B12 of the virtual address will have control on the C bit of sitting, and the block offset will not be interesting for us. So to find congruent addresses, we will need these 4 bits of physical plus the 3 of the virtual one. So if one attacker takes 2 random addresses with the same offset, the probability of having congruency will be 2 minus 7 in this case. So if we use this probability to have an estimate of how many addresses we need to get randomly to find one eviction set, meaning 12 congruent ones, we will get to this chart, which means that if we get 1,000 addresses with the same pay offset without any kind of information about heavier bits, this 1,000 addresses, the probability of them being for the offset the probability will be low. If we do the other way, the probability will be higher. Having said this, it is more difficult to find smaller eviction sets than bigger eviction sets, but we didn't see anything about how we can find the smaller ones. The first idea could be, therefore, well, we simply get direct address associativity 12 until we find a minimum size eviction set. But the probability is 2 minus 7, 2 minus 12, so it is never going to happen. Or if you're lucky enough, you will probably come across it very rarely. So what the problem is that you can find it. So people use an algorithm as follows. So we cannot find congruent address, but we have RT. So what we do is we get a big eviction set, and then we use this test in order to reduce it. So the algorithm is very simple. So you start by an eviction set, you get an address, and then you test, and you see whether or not this remains as an eviction set. If it is not, you discard, and you get one more. So you get addresses, you reduce the size until you don't have an eviction set. So what you learn is that the address you got is part of the minimum eviction set. So you use it and you repeat it. So you repeat the process until you find associativity of address and you have a minimum size eviction set. But if you look at the cost of this algorithm, you see bad because it's very difficult. So 4K pages with 3,000, you will get an eviction set. So 3,000 quadrupled can be possible. But if we look at an environment, instead of having 4B pages, we have information of pay offset. So the size of addresses you need in order to have a reasonable possibility of having an eviction set is 30,000 or 90,000 rather. So, and this is going to be very difficult, especially if you want to do things fastly in order to avoid attacks. So we need to improve this. So we need to solve optimization problem, which would be as follows. It is very easy to find a big eviction set, but this is quadratic to reduce it. It is quadratic to reduce it to its minimum core. So we have eviction. How many efforts you need to find a smaller eviction site will be costly, but the quadratic reduction will be faster. So the first approach would be to solve this optimization problem and find the optimum size in order to minimize efforts. The other possibility is, instead of getting one-by-one address, you take groups of addresses. So in addresses, so the algorithm is going to be faster, but the cost is still quadratic. In order to improve this, therefore, is when we use Syphilis. So as it turns out, the history of Syphilis is as follows. During the war, the army wanted to see what soldiers suffered from syphilis, to treat them and not to die, meaning not to die from syphilis, but die at war. But the idea was you get blood from a sample, blood from each soldier, and you analyze the sample. The problem is that if most of soldiers are infected, this becomes an efficient process. But if most of them are okay, you're spending a lot and your approach is not efficient. So at that time, testing was very expensive, so it wasn't okay. So Robert Norman decided to group tests. So for syphilis, the test is sensitive enough. If you group many blood samples, even if there's one affected, the result is going to be positive, and the other way around. So you test the group. If the result is positive, you don't learn anything, and you will have to split it into some smaller group. But if it is negative, you can discard many of them. So what Dorman said, who was a mathematician, was to find the optimum size groups in order to identify the infected members of this population or cohort, and to get a positive thing. So as a result of that, a branch of mathematics combination was created called group testing. Group testing can be applied for many things, and I had no idea about this up until last year. So this is used by pharmaceutical companies, for industrial companies, for cryptography issues, and I was not aware of this at all. So they could be used for this. So if you want to identify faulty light bulbs, you take the test, and up until the bulb, none of the bulbs is okay, so the test is positive. So in the case of basic grouping, if you want to identify an element within a population, majority or minority, this is logarithmic cost. If you want to identify D elements in a population, you make a logarithm search multiplied by D. So what you get at the end is log n D by 4, divided by 4. So based on this very simple group testing definition, as time went on, the problem and the variants have been generalized, and I came across something very interesting called threshold group testing. So this definition was used to the same thing. So we have a cohort, a population, and we want to identify faulty elements with a smaller number of tests possible. But the difference is that this test will be positive if the number of faulty elements is higher than X value, and the test will be negative if the number of faulty elements is lower. So if the number is in the middle, the response is arbitrary, and we know nothing about it. So this was used by us to see if a test was an eviction test. So if we have congruent address is positive, associativity, the test will be positive, and if it is lower, the result will be negative. So the test is called threshold group testing without gap, because there's like a midterm thing with no result. So we have OD log, it can be used for n number of tests. So it is not a binary search. The particularity of group testing is the faulty element could be diluted enough so that the two tests result in negative results. So you cannot use either or. So this is more complicated. So L equals U minus L is okay for that. So I found out that the problem I wanted to sort out to find eviction sets was done by a branch of mathematics that has been used for 50 years. So I tried to find an algorithms to reduce eviction set in an efficient way. So the difference is that group testing tries to minimize the number of tests, but I wanted to minimize the number of memory access. So number of tests by the size of each test, basically because our test allows us to access all the elements of the group of addresses. So with this very simple algorithm, we will have linear cost instead of quadratic cost. So we have a big eviction set, and we split associativity per minus divided subgroups. So with this division, we have associativity in ensembles, which will result in eviction set. So n divided by associativity plus 1 association. So imagine we have 200 addresses, and we have associativity 4. So we want to find an eviction set, a minimum eviction set of 4. If we divide this in 5 sets, so these 4 elements will be united somehow, and the 4 will be contained, will be included. So this is a little bit of the definition of this algorithm. So I created a small tool on C to allow you to test different algorithms and different strategies, different parameters, etc. So 3,000 random blocks with a cache size 6. So using group testing algorithm, this is just a strategy. Associativity 12, offset, number of repetitions for each measure of time, threshold to make the difference between cache hit, cache mix, if it is in the cache or not. So many things. So you execute it, you execute all the things, you find an eviction set. U is used to know whether if an eviction set is an eviction set. So you translate virtual eviction to virtual eviction to physical eviction, I'm sorry, and then you find all the different caches. So everything is okay, but it is okay because when we can run this faster, you can solve. With this algorithm, you can reduce actually groups of 9 or 120,000 addresses in few seconds, and before it took us minutes. So what happens with the GS? You can use it by using a navigator where attacks are harder to deal with. So what can we do all this thing with JavaScript? So when I'll be based on Chrome, but the ideas could be generalized. So Chrome is a multi-process thing. Each tag, each security domain will be running its own process in the operating system, in isolation. So the distance will be V8. V8 is the engine of a Chrome, JavaScript, Nova, etc. So an engine or JavaScript modulator, whatever you can call it. So the V8 has been simplified. Before, there were more compilators. So depending on how you were using, it was compilating when one thing or the other. So you take a text, the navigator will have a JavaScript text sent to V8. So the text will be sent to many places, and there will be two processes. Ignition on the first one that generates a bytecode in a very fast way, very efficient, and then it interprets it. But the idea is when you upload a page, you will not spend time to compilate JavaScript, but you start compilating as soon as you can. So TurboPan is the compilator, which is the just-make compiler, which will be the optimized compilation. So on JavaScript, when one function starts heating, as we call it, the compilator will start optimizing it. But how does it do this? JavaScript is an encrypted language, meaning each type with each function operation, the variables can be of many sizes: stream, object, networks, etc. So it's easy to think about this at a high level. So operator must know if it is stream, catena, or a number. You add or you create something else. But when you generate a specific code for that, you should run checks on runtime in order to see what kind of datum you're using to come up with one function or the other. So when x86 would generate very simple JavaScript codes, you will have a lot of things that will make the function to run very slow. So it optimizes the compilator. So we use hints, meaning the type of data used by a function, and the other part, which is basic for me to understand what JavaScript compilators do, is as follows. When you're compiling, the compilator will come up with a static analysis of the code and come up with the following. You have an operator or a function that makes me always back to the same type. Operator per on JavaScript, it depends on the kind of access. That will always be an enter. So the compilator will be searching this kind of thing, and it will decide that at this variable, at this point in the execution flux, it will have an entire. So when you identify these things, you cannot identify a great number of runtime checks. You will generate one thing for an entire process, because you can decide that for a variable, from this point on, something else will happen. Otherwise, you will have a security failure. So this is the idea. This is the main idea to optimize JavaScript code. Have you ever heard of assembly JavaScript? This syntax that is the puts operator or with a 0 and then all the variables? Well, basically, this is to explicitly make that after the different compilators, static analysis, you can have all the variables as entire elements. The compilator will be using all these entire elements, which will make things very easier. So this is a great idea, and everything went well up until came up with another kind of compilator, GIA to JavaScript, and things became more complicated, but it is better to compile different things. It's still a hack, though. It works, but if you can do things in a cleaner way, much better. The thing is that we have WebAssembly currently. So hackers started to think about this seriously, and they said, okay, it's okay to have a static kind of compilator to execute things with negative performances. So they created WebAssembly, which is a language that seems to be an assembler, but it's integrated in all JavaScript engines. And you have to know that it uses stack machine. It's a Harvard architecture, meaning the code is separated from the memory, which makes things very more simple. So it's a statically typed languages, 62, 60, 86 bits. So no route should be inserted by the compiler. So X expressions. We are going to see syntax afterwards, but it seems simple. at the beginning. When you have a stack machine, and if you read instruction in a flat way, it's very difficult because when the stack is full, operations start to separate. So with X expressions, you can animate these operations and make your life simpler. But the most important thing, for me at least, and I guess for other people, with WebAssembly, you get more performance and predictability of the execution. The execution time will not depend on the other things JavaScript is using, compiling this action, garbage collection on the other part, or optimizing a function, because JavaScript is using do I optimize or not in order to press the memory a little bit. So with WebAssembly, you generate a code, and the code is already optimized. So it's simple. And then lift up versus turbofan is the same thing that we had with Ignition. Just out of curiosity, Ignition generates bytecodes very fastly, but it's not efficient. Liftoff, same thing. You compile a passive WebAssembly, a code that could be executed swiftly if you're interested, and then on the background, when you generate a WebAssembly code, you will start using turbofan. So once you get turbofan, you will not use liftoff. But if you want to optimize things swiftly, you use liftoff. So this is JavaScript, and how it works to generate codes. We are really interested in knowing how the memory works. I'm not going to explain all this into all the details because I don't know much about this actually, but you have a lot of allocators, and they are constantly being changed. Before, we used a partition and then oil pan and parts depending on the objects you're working, garbage or not, garbage collection, and the other one and the others are not. In the case of V8, to my knowledge, it uses the memory by itself. And the last thing is they included RootedCON, which is a garbage collector. Again, what is interesting compared to what we had before is that this concurrent, before you had to stop JavaScript and leave the garbage collector to stop whatever it wanted. With RootedCON, you have a GC, which is the garbage collector, so you're blocking things because you need to introduce blocks, but not like in the past. So V8 has different regions depending on the types you use, depending on the objects you want. So we're going to focus on large object space, this region. And the interesting thing is that when you try to reserve memory with buffer, or something that is bigger than the region itself, so this large object space will delegate the response in the operating system, I'm sorry. So you get strays with V8, and you try to get this kind of buffers up until the moment it will be using map directly. So it's a virtual map, so the page on the operating system will be aligned. The offset 0 of this page will have the 12 element 0. So you can control page offset if you have a location which is big enough. So you get the virtual memory, you will have the 12 page offset of the physical page. So what do we miss now? What is lacking to close the loop on JavaScript? A high resolution clock, so that we can differentiate between cache or memory counters. So high resolution of time we had before, but as a result of this kind of packages, so we have been reduced this. Instead of that, there are simplification techniques. So you have a counter or clock to amplify the precision of the clock, and you can make tricks to get to the difference. But the best thing is to use shear array buffer. I don't know if you know about this. When T3 were created, navigators said to enable this by default. But this is an easy way to have a high-resolution clock on JavaScript. You have a shared memory, you use the thread, and the thread will run a counter that emulates the clock. So it is a loop. To increase things, you will have a cycle, so each augmentation means a cycle, but it is the same thing. So last version reactivated this because most of developers wanted this, and because deleted this make life of the attackers very difficult, but not as much as needed. So this is an example of the code on JavaScript. So like a worker. So we have the worker, and when it gets a message, it will start wide and true and increase the counter. And this will left run the main code here, the worker here, the allocation of shared memory, and the reference is passed on to the memory, and this increases, and here this is how to measure time. So we execute the function to measure time, we access again, and we get the difference of the counter, which will produce the difference. Let's talk about a little bit of code to conclude. For those of you who are not aware of all that, this is something probably new. So these are modules. So the idea is to import a shared memory here. We export the access function, and this access function will get a parameter entires, and then it yields an entire. So we have a load using the memory we imported, and then return. So how do we, something I forgot before, WebAssembly has a binary method, which is good because you don't have to send text. But this binary system is been thought for being used on streaming only one pass. So you use WebAssembly, and the navigator will generate things automatically, so we accelerate things. So with WebAssembly, which is a tool of WebAssembly, we compile this little software, this little program, and then the shared memory in the version I was using is not by default, so we distance the WebAssembly module, and we execute the function we exported, access, and we can have access to 0, offset 0. So for V8, this is a VHL with a small environment. Same thing with OD, E, and Chrome. Flax, same thing. I did this way because it's more comfortable for me. So we have this flab of print code and code comments. So when we execute this function, the screen will show as the code created by TurboFlap, because it generates native codes that looks like that. This little function here will be translated into this code here. So RSI has always WASM instance, so the offset of memory, offset of the external functions we imported, parameters, return by racks. This is the prologue. The RSI is included in RDX. This is the memory offset. I'm sorry. So we have comparisons here. Racks is our offset for this function here. So we have the comparisons of signs here. The one that is highlighted here is access to memory. So RBX, which was the memory offset, plus the RDX of our racks. That was our offset before. So now we return, which is a little strange here, but we know how the compiler works. So this is how to set up the JavaScript compilators, and we use this web asset to clean a little bit. So if you include the I62 or the I32, you delete this comparison. I wanted to delete this to avoid noise. So if you include a series of 1 masks, there will be no sign comparison, because the sign is determined by the heaviest B. So when you use the application, the machine is smart enough saying that this number after applying mask will never be negative, so why sound check over there? So the idea is that we can play with WebAssembly to generate a x86 clean. That is clean.
And here we have the same loop of increments we saw before, but now we're talking about WebAssembly. We have a loop, and as you know here, it's clearly seen. Offset 0 contains a counter, so load offset 0 plus 1, and this storing offset 0, and that's it. Then we get a code. This is quite shorter than what we had in JavaScript. Another alternative is to use extensions, as it is a shared memory. We could use this for atomic instructions of WebAssembly. I tried it because I've heard that for high precision, high accuracy, that was better, but in my case that was not valid. So I always use the version that's not the atomic version. And well, those functions here, that's one of the most important ones, as we see here. And the reason is that I represent this as we see here, the tests are conducted in all addresses, and I go across the list. I use it instead of having the non-direct list of offset. We have access only to those that I want to test. I'm using here, for instance, odd things. This is to clean the thing, and the interesting thing is that there are 2 ways to have access to the eviction set. One is using this linked list where you do not introduce noise, and it is the logic of the software to test things. But then all the access to memory, well, it depends. Once you have the access, then you know which access you will have to which direction afterwards. If you have 1,000 addresses, you have 1,000 times access to the memory. And if you talk about it, then you will use the execution we mentioned before, out-of-order execution, where you could have several in parallel. In my case, in my implementation, I prefer the slow option, but where I introduce no noise. Another option is to, as we see here, to deploy this list that is linked and to use them at the same time to parallel access, or 4 in parallel. So in the end, we'll use a trick and we will divide by 3 or by 4 execution time. We will save time, we will speed it up. And here we have to measure the time to access. In this case, we have the WebAssembly module, and we're going to try to have an access to the victim address. We're going to have access to the clock or to the counter. We will go back to the victim and we'll measure the clock, and we will see the difference in those 2 clocks. If we do it the way we saw at the beginning, we would have a code as you see in blue. It seems quite well clear. We see the mask we mentioned before. Memory access here, we have the time to start. Memory access to see the hit time, and here the end time and the final. And we see here that we haven't got any, well, there's no correlation of data. Those loads won't be in the order you would like them to pass. those instructions could be executed in a parallel mode. It could be that the buffer, once you have the request to the same address and you have the request twice, they will say, no, I give it the same twice. So it is up to the hardware. It won't say, why shall I do it twice? I'll give you the same value. And you will have zeros all the time because you're controlling differences. And when you establish a difference, you will get zero. You won't see anything, you won't learn anything about it. And then we add differences artificially. This is what I did here. What I did here is that the value that I take from the first load, I will be using this when it's an operation that won't be affecting the offset of the second load, but this is going to be interlinked, and this is going to be executed in the order we want to have. And then the truth is that in this case we measure the hit. If we want to see eviction here, what we have is we add the function we mentioned before, and we have access to the victim that is in the cache memory. We have the traverse here that will affect a victim or not, and we have to measure the access to the victim, and we measure the time, and that's it. I have time for a demonstration, and as we have time, demo on. No, I'm going to play some music. The music is not because I love music, no, it is just to stress the CPU, because what you want is to have a practical attack. So you have background noise at the same time, and trying to have an access to the browser. I'm going to do it from another one. I'm going to have minimum changes, and then I have several browsers on, so I'm going to do it now, and let's see what happens.
Bueno, pues lo bajo un poco.
Well, basically, this is the code. JavaScript, the algorithm I was mentioning before, and you prefer to turn your back while reading this?
Este es el módulo de WebAssembly.
This is a WebAssembly module. This is what I said about the test. We have the access to the address. We measure the time afterwards, and as we see here, how difficult. I'm going to start retrieving. Sorry. I'm going to take only one eviction set first. I'm going to take out only one. Let's see what happens. And what I'm going to try to do, if I have a command here, let's see if I can find it, is we're told here that I use it for debugging purposes. I have a print debug of the WebAssembly instance, and what's interesting is, let's see what happens. I have here, let's see if you see memory start here. Yes, that's the offset of the array, memory array that's been used to get the virtual address, and to see that the offset I've found is the eviction set. And those are the offsets. My cache memory is 18 addresses, 18 associations, and we have to see the offsets within the array. We have a small script here, the small script that I'm showing you now. Let's see. I have a small script. And the only thing is that we're going to see the output. We will calculate the memory start. We will add up offsets. And I have a C program where I have the process ID. I give the virtual memory as an input, and I get the physical address. And out of the physical address, I can calculate a slice, and I can get my answer of a cache here. So this has been checked, verified. All the addresses go to the same eviction set, of the same slides. And now we're going to perform the same thing, but now instead of finding only one eviction set, now we're going to find all of them, almost all of them. And okay. Basically, this is what we found here in 15 seconds only. Those eviction sets, different eviction sets, and we have 128. In cash, we have 8,192. But if you take 128, you can offline calculate the proper offset for the 8,192. If you get 128 eviction sets, you have eviction sets for all the cache memory, and that's it. And that's it. That's it, folks. That's it. Thank you very much.